Hello, I'm Seema and welcome to part 3 of the chapter Chemical Reactions and Equations. In this video, I'm going to tell you about chemical equations. In the previous videos, we discussed what chemical reactions are, how reaction substances react with each other and they result in the formation of certain substances which are known as products. Now the method in which we write these and we represent these changes on paper are known as chemical equations. So the official definition of chemical equations will be that the method of representing a chemical reaction with the help of symbols and formulae of the substances involved is known as a chemical equation. In order to understand this definition, we must know what symbols and formulae are. If you would have seen in your chemistry book, for different elements we have different symbols of elements, and I'm sure you've studied this in your class 9 also. For example, zinc, the symbol of zinc is Zn. For hydrogen, the sign is H. For sulfur, it is S. For oxygen, it is O. So all elements, they have certain symbols, and those symbols, they are 1 alphabet, 2 alphabet, and in some cases, they are 3 alphabets. These symbols, they tell you that it is an atom of that element. But these atoms may not be present in the form of atoms in nature, and they are usually present in the form of molecules. So when they form molecules, the molecule of any element, it could be one element, it could be more than one element. These molecules together, they cannot be represented by single symbols. And a molecule is represented by what all elements are present in that molecule and how many atoms of which element are present in that molecule. You can have monoatomic molecule, you can call it a molecule although it's a single atom. So zinc remains as zinc, therefore in the solid form, therefore we just write Zn, and this means it is zinc. You can call it an atom of zinc, you can call it a molecule, you can call it the symbol, or you can call it its formula. So the formula is when you represent a molecule of a substance, and the symbol is only is the identity of an element, of one atom of an element. So when we say that representing chemical equations or reactions in the form of symbols and formulae is known as a chemical equation. So what do we see in this particular reaction that I have given you? You have zinc, and which combines with H2SO4. Now this has 3 elements in it: hydrogen, sulfur, oxygen. And when you have 2 hydrogens, 1 sulfur and 4 oxygens together to form one molecule, that molecule is known as sulfuric acid. Right? It is known as sulfuric acid, and this sulfuric acid is now a molecule, and you have symbols of 3 elements, but this is the formula. H2SO4 is the formula for sulfuric acid. So what did we do? We used the symbol for zinc, the formula for sulfuric acid, and we got zinc sulfate. Zinc sulfate, now is it a symbol or is it a formula? Now we have zinc, we have sulfur, we have oxygen, and in certain ratios, 1 atom of zinc, 1 atom of sulfur, 4 atoms of oxygen. So together they make the formula of zinc sulfate and hydrogen. And when we write the symbol of hydrogen, it is H. But when we write 2, it means a molecule of hydrogen has 2 atoms of hydrogen. Therefore, this is not just a symbol, it's a formula for hydrogen. Because the molecule of hydrogen is represented by the symbol H and with the subscript 2. What is a subscript? Something that we write below a symbol. That is the subscript. Under it we write it has 2 atoms of hydrogen. One molecule of hydrogen has 2 atoms of hydrogen. So this makes it the formula of hydrogen. Having defined this, what are symbols and formulae? Now that you've understood it, writing down chemical reactions with the help of these symbols and formulae is known as a chemical reaction. That is the definition. Now let us look at this reaction. We have zinc. It combines with sulfuric acid to give you zinc sulfate and hydrogen. I could have written this in a sentence, zinc combines with sulfuric acid to form zinc sulfate and hydrogen. That would take much longer. So this is a way to make our work easier, and it's a shorter way of writing down the reaction. And also, when we write reactions in the form of chemical equations, we can make it much more informative. It can tell us much more than what a worded sentence would tell you. For example, when I say zinc combines with sulfuric acid and gives us zinc sulfate and hydrogen, I spoke the words, I wrote the words, but from those words, would you be able to know that sulfuric acid is actually H2SO4, that zinc sulfate is actually ZnSO4, that there are 4 atoms of oxygen, 1 atom of sulfur, 1 atom of zinc in 1 molecule of zinc sulfate? Would it be able to tell you that hydrogen, a molecule of hydrogen, actually has 2 atoms of hydrogen? So if you really see the equation, it gives you a little idea about the molecules and the formulae too, which is very helpful in chemistry. Now let us take an example. That I take hydrogen and I take oxygen, and I know hydrogen and oxygen combine together to form water. So I take both of these in a jar and I seal the jar. I took both the gases, 1 gram of one, and let us say measured masses of both. And then I seal the jar and I give it the conditions under which hydrogen and oxygen react together to form water. Tell me logically, when I started the reaction and I sealed the jar, I weighed my jar. And then I carried out the chemical reaction and I got water from the hydrogen and oxygen which was present inside the jar. So after the reaction, if I now weigh the jar again, will the mass of the jar change because the reaction took place, or will the mass be the same? Logic, what does it tell you? In a basket, let us say, what we can represent these chemical reactions in the form of baskets of apples, and let us say in one basket I have a banana, I have an apple, and in another basket I have a pear, let us say, and I have grapes. Okay? Now these are my reactants. And they reacted and they resulted in the formation of 2 products. And what happened? I took the mass of both the baskets, whatever was the mass. The total mass, let us say, of these baskets was X. Whatever was the mass, the total mass of all the fruits in both the baskets, all the reactants, let us say it was X. Let me just mention this one point also. All the substances that react, they are known as the reactants. And after the chemical change takes place, whatever is formed is known as the product. So you may have more than one product, so they are called products, and these are reactants. The reactants are shown by symbols of plus, that is this and this and this, all the reactants are summed up. And the arrow shows that the reaction took place, and on whatever you have on the right hand side, they are the products, that these were the things that were formed. So in this reaction where we took 2 baskets and we had fruits in them, we now get 2 products. And this time I again have 2 baskets. And I have the banana here, but the grapes, they came here instead. It's the same. I don't rely on my diagram skills. I'm not very good at making them. So what happened now when the reactants, the substances, they exchanged their places. That is what happened here also. If you really see, you had zinc standing alone and hydrogen, sulfur and oxygen which were bound together in a molecule. But when products were formed, zinc combined with sulfur and oxygen and hydrogen was thrown out. So the same thing is happening here. The banana and the grapes came here, and the pear and the apple, they came on one side. Now tell me, logically, if you weigh, what has happened here? The things have just moved from one place to the other. So whatever was the mass of the reactants, what according to you logically should be the mass of the products? If the mass of reactants was X, the mass of products should also be X. This is known as the law of conservation of mass. The mass of substances in chemical reactions, it is mass never changes. The total mass remains the same. So law of conservation of mass, the statement of this law is that matter can neither be created nor can it be destroyed. It can only change its position. Let us say, instead of this, there was an apple and there was me, right? An apple and this is me. I ate the apple. So the mass of apple plus me should be equal to me with the apple inside me. What would the mass be? The mass would be whatever was the mass of the apple plus me. The mass here should be the mass of the apple plus me. It should be the sum of the two. So ultimately, mass should be conserved. This is known as the law of conservation of mass, that matter is neither created nor destroyed. It only changes its position and therefore mass remains conserved. And this is what has to be, and why am I talking of all this when I'm talking of chemical reactions? Because when you have reactants and products, you must have the same mass on both the sides, because you cannot lose mass in a chemical reaction. And that is why we call it chemical equation. We call them equations. Why? Because both the mass on both the sides should be equal. The number of atoms of each element on both the sides of a chemical reaction should be equal. And that is why we use the word equation. They should be equal. So whenever the number of atoms of each element in the reactant and the products are equal, that is what would be a correct chemical equation. And such chemical equations where the number of atoms of all the elements on the reactant and product sides is the same is known as a balanced chemical equation. Such an equation is known as a balanced chemical equation. Let us take the example of this equation that I am telling you about. Here, let us take, what do you have on the reactant side? Which elements do we have on the product side? On the side of the reactants, we have zinc, hydrogen, sulfur and oxygen. And on the product side also, we have the same elements, that is zinc, hydrogen, sulfur and oxygen. Let us count the atoms of each of these elements on both the sides, on the reactant side and on the product side. On the reactant side, how many zincs do we have? 1, right? And on the product side, oh, the pen is not working. So we have 1 atom of zinc on the reactant side. On the product side, we have 1 zinc, okay? Hydrogen, we have 2 hydrogens here. And how many hydrogens here? 2 hydrogens here. How many sulfurs here? 1 sulfur here and 1 sulfur here. Do you see? How many oxygens here? 4 oxygens here and 4 oxygens here. So looking at this, what do we see? We see that the number of atoms of each element on both the sides of the reaction in this particular equation are the same. So we say this chemical equation is a balanced chemical equation. There is balance of mass on both the sides. It's a balanced chemical equation. On the other hand, what would an unbalanced equation be? If this is a balanced equation, let's take an example. We know, I told you, that we took hydrogen, we took oxygen, and it resulted in the formation of water. Now, I've written this, that this is hydrogen, this is oxygen, and it resulted in the formation of water. So do we see, let us check if this equation is balanced. How many atoms of, now what do we have? We have hydrogen, we have oxygen. How many hydrogens on the reactant side? We have 2 hydrogens on the reactant side. How many hydrogens on the product side? 2 hydrogens on the product side. So it's balanced. Hydrogen is balanced. Oxygen, we have 2 oxygens on the reactant side, but only 1 oxygen on the product side. Do you notice? So if we started the reaction with 2 atoms of hydrogen and 2 atoms of oxygen, and we got a water molecule which had 2 atoms of hydrogen and only 1 atom of oxygen, how do you report for that 1 oxygen which is missing? Where did that 1 oxygen go? It is unreported. We have no idea, and that does not happen because oxygen is not a ghost. It's not going to vanish. It is, if it is not here, it means there's something wrong with your equation. The equation is not balanced, right? So such equations where the number of atoms of each element on both the sides are not equal would be called an unbalanced equation. In the next video, I'm going to teach you how we can balance equations, because unbalanced equations do not make sense according to the law of conservation of mass. And it only makes sense that whenever we write equations, we should always balance them. And our equation finally should be a balanced chemical equation. Right? So the next video would be for balancing of chemical equations. But right now, let us move ahead with our knowledge of the chemical equations. What more should we know about chemical equations? What else can an equation tell us? Do you know we can make chemical equations more informative? It is not necessary that we just write only the reactants and the products, the symbols and formulae, and that finishes it off. A lot of information can be added to the chemical equation by just adding that information a little by little. So what are the 3 ways by which we make chemical equations more informative? There are 3 ways how we do it. The first is that we can indicate the physical states. We can indicate the physical states of substances. You can make equations more informative. You can indicate the physical states, you can indicate the heat changes, and the third is that you can mention the conditions of a reaction. But let us come to these one by one. In heat changes, there are 2 types, that is exothermic and endothermic reactions. Let me start explaining this to you now. How do we make equations more informative? We wrote this reaction here that you had zinc, you had sulfuric acid, it resulted in the formation of zinc sulfate and hydrogen. Now we know that hydrogen is a gas, zinc is a metal and it is a solid. Sulfuric acid is dissolved in water and therefore it's a liquid. And when a substance is dissolved in water, it appears to be a liquid, but it is actually in the form of a solution. And any solution in water is known as an aqueous solution. So we can write the physical states of the reactants and products, that is, whether they are elements or the compounds. The physical states of those substances can be written after the formulae. Now that is what we have done in this reaction. We had zinc, and with a small bracket, in small letters we write S. It means that zinc, we have it in the solid form. Sulfuric acid, we put a bracket and we write AQ. AQ means it is aqueous. It is the sulfuric acid molecules have been dissolved in water. It is present in a medium. So we have sulfuric acid which is aqueous, and you get, as a result of this reaction, we get zinc sulfate which is aqueous again. So we write it is dissolved in water, so we write AQ, and hydrogen which is produced as a gas. And therefore, when you really look at this reaction, it is like you put zinc granules in a jar and you have sulfuric acid which looks like water because it's a liquid and it is dissolved in water, and when the reaction takes place, zinc sulfate is formed which dissolves in the water, but you see bubbles of hydrogen gas coming out of the jar. And why bubbles? Because the bubbles are actually of the hydrogen gas which form bubbles and they escape from the liquid, because gases are lighter and they travel upwards. So we can make a chemical equation more informative by writing down the physical states of the reactants and products. There's another example here. We take slaked lime, and slaked lime is calcium hydroxide. It is also called lime water. And lime water, when it is dissolved in water, it is an aqueous solution of lime water, and you pass carbon dioxide gas through it. Do you know you take lime water in a jar and use a straw and start blowing into it, because we know we blow out carbon dioxide. So when you start blowing out into it, you're giving carbon dioxide gas to the lime water which is aqueous. It is like taking, don't you do that when you were kids? You blow into your Pepsi when you're drinking it. It's somewhat similar. You have lime water and you start blowing into it, and that gives carbon dioxide gas to the lime water. And we notice after some time the lime water, it starts becoming cloudy. It becomes, you see, it's turning white. It starts turning milky. That clouding, we call it, it's turning milky. And why does it turn milky? Because a reaction takes place between the calcium hydroxide and carbon dioxide and results in the formation of a white product, which is calcium carbonate. Calcium carbonate is the chalk that you use on the blackboards. the white chalk. So calcium carbonate is a white precipitate. Now what is a precipitate? A precipitate is an insoluble product which settles down at the bottom. So a precipitate is formed, which is white in color, and water is formed, which of course dissolves in the water because the solution was already aqueous, so you don't know where that water goes. So what do we notice? That when you put carbon dioxide through lime water, it turns milky due to the formation of calcium carbonate, which is a precipitate, which means we started with an aqueous substance and we mixed gas into it, which resulted in the formation of calcium carbonate solid and water, which is a liquid. So by just writing down these, we are giving information about the physical states, how the reactants and products are present. The second way of making equations more informative is by telling, usually whenever chemical reactions take place, either they absorb heat or they give out heat. So heat changes usually take place with chemical reactions. Now chemical reactions in which heat is given out are known as exothermic reaction. Therm means heat, exo means exit. So therm, exo means exit, therm means heat. So exiting of heat. When in a chemical reaction heat is given out, the reaction is known as an exothermic reaction. And when in a chemical reaction heat is absorbed, have you seen come indoors? Don't we say come on, come indoors, indoors, endo. Endo means coming in and exo means going out. So when in a chemical reaction heat is given out, it is an exothermic reaction. Therm is heat. And when heat comes in, that is heat is absorbed, the reaction is known as an endothermic reaction. This information can also be added in the chemical equation because this is an information which would be very important to someone who is going to perform an experiment. If you are supposed to, you're carrying out a chemical reaction which needs heat and you decide it's a very hot day, so why don't I carry out the reaction in a refrigerated room? Let me just go and put it in a refrigerator and carry out the reaction. Let it happen inside the refrigerator. So you might want to just put the substances in a refrigerator because it's a warm day, but the reaction was a reaction which would have taken place if it absorbed heat. It was an endothermic reaction. Will the reaction even take place? No. So knowledge about the heat changes which take place in a chemical reaction are actually important, and this information can be added in the chemical equation. How do we do it? If the reaction is exothermic, if heat is being given out, we write heat in the products. We usually write heat in the products. For example, carbon combines with oxygen. Now, this has got more information. It has the physical states also. Carbon solid combines with oxygen, which is a gas, to produce carbon dioxide gas. And in this reaction, heat energy is given out. Now remember, it is not just heat which is given out. Sometimes energy can be in the form of sound. It can be in the form of light. Have you seen when you burst crackers and they make that loud sound? That is energy being given out, only it is in the form of sound. Energy is not always in the form of heat. So we can say that it is an exothermic reaction and it is heat energy which is given out. Sometimes we write only energy, right? So carbon solid combines with oxygen gas to give you carbon dioxide gas, and this is an exothermic reaction, it also gives out heat. As you come to the next grade, you will realize you will start specifying how much heat is given out. There's a measure for everything. Okay, heat is given out. How much heat? So you usually write the number of kilojoules of heat given out in this reaction. So that is also usually done, but at your stage in grade 10, you just need to know that heat is added in the products. Similarly, there are two more examples here. You have methane. Methane is it is natural gas, methane. So methane, which is natural gas, it burns in oxygen to produce carbon dioxide and water. Now this equation is also, all these equations are balanced, but we'll go into the details of balancing of chemical equations in the next video. Right now I just want you to focus on the fact that physical states are given, the equation is balanced, and heat has been given in the products, which means that this reaction is also exothermic. The next reaction is where you have glucose combining with oxygen to give you carbon dioxide and water. There are two processes which are opposite in nature. You know that plants produce their own food by the process of photosynthesis. And what happens in the process of photosynthesis? You have, it takes carbon dioxide from the air, oxygen which is present in the air, and in the presence of sunlight, it takes water from the soil, that is, it absorbs the water from the soil, which we water a plant, it takes in water and it absorbs carbon dioxide from the air, and it uses the sunlight. In the presence of sunlight and in the presence of certain molecules which are known as the chlorophyll pigment which is present in plants, they can produce food. So carbon dioxide combines with water to produce glucose. In the case, glucose and oxygen is also produced in this reaction. So that is why we say plants give us oxygen. How do they give us oxygen? They use the water, they use the carbon dioxide, and in the presence of sunlight and chlorophyll, they produce glucose, which is food, and oxygen, which helps us to breathe. The opposite of this takes place in our body. We eat that food that we got from the plants, that is glucose, and when we eat that food, glucose, and we breathe in, we take in oxygen. The oxygen now combines with the same food and the opposite reaction takes place and results in the formation of carbon dioxide and water. So when we exhale, what do we exhale? Carbon dioxide, and the water, of course, it goes into our body, into our bloodstream, and then is excreted out of the body, and it gives out energy. That energy we say in the form of chemical energy, which you'll study in your biology classes. So this process is actually respiration. So respiration is a process in which glucose combines with oxygen to produce carbon dioxide and water, and energy is released in this process. And the opposite of this was photosynthesis, where you had 6 carbon dioxide molecules combining with 6 molecules of water to produce glucose and oxygen in the presence of sunlight and chlorophyll. So what kind of a reaction is this? If they are opposite reactions. If in this reaction energy was given out, in this reaction energy is being absorbed. And where is the energy being absorbed from? From sunlight. Light is the source of energy here. Because energy can be in different forms. It can be in the form of light, it can be in the form of heat, it can be in the form of sound. So in this case, it is absorbing energy from the sunlight. And this is photosynthesis. Photosynthesis. So these are different, and if respiration is an exothermic process, photosynthesis, being the opposite of it, is an endothermic process. So let us now come to a few examples of endothermic processes in which heat is absorbed. Nitrogen combines with oxygen, nitrogen gas combines with oxygen gas, and it absorbs heat to produce. So when you're writing heat, you're reporting heat in a chemical reaction, you must write heat on the reactant side. So for exothermic reactions, heat is written in the products, and for endothermic reactions, heat is written in the reactants. And it results in the formation of 2 molecules of NO, nitrogen monoxide, which is a gas. Calcium carbonate, which is a solid, I told you chalk, when you heat it up, it breaks down into calcium oxide and carbon dioxide. Calcium oxide is a solid and carbon dioxide is a gas. And how did you break the molecule down? By heating it. So you gave energy. It is an endothermic process. Calcium carbonate absorbs energy and it breaks down into calcium oxide and carbon dioxide. And of course, I told you about photosynthesis. Now, what do we understand? How did we make equations more informative? We discussed only 2 steps. 1, we wrote down the physical states. Secondly, we wrote down about the heat changes that took place, whether the reaction is endothermic or is it exothermic. The third way to make reactions more informative is to write the conditions of a reaction. What were the conditions under which the reaction was taking place? Could we have put it in the fridge and carried out the reaction? What was it being held out in the open? Was it the atmospheric pressure that was working on it, or did we put the entire reaction mixture into a jar and we had a piston and we were pressurizing it together? You know, when you have Pepsi and you open the lid of the Pepsi, the fizz of the Pepsi, that is the cold drink of a soda, it comes because when you just open the lid, the gas has been pressurized into the liquid. So what were the conditions under which this happened? If the person who is making the soda doesn't even know that gas has to be, carbon dioxide has to be pressurized into the liquid, when you open your soft drink, there will be no fizz in it and there will be no fun in drinking that kind of a soft drink. So whatever chemical reactions are taking place, you can make it more informative and more useful by writing down the conditions of the reaction under which the change took place. Let me write down a few examples and then I'll explain it to you. So let us now do the third way how equations can be made more informative. As I told you, you can make equations more informative by indicating the conditions under which the reaction took place. Now we have three examples here. You have potassium chlorate, KClO3, which is solid, and how do we show the conditions of a reaction? We write the conditions of a reaction above and below the arrow mark. Did you notice here when I wrote the equation for photosynthesis, I wrote the condition sunlight and chlorophyll above and below the arrow. And at that time, I chose not to explain this to you because I knew I'd be explaining it here. The conditions of a reaction are written, these reactions, they take place under these conditions. They only take place when these conditions are fulfilled. And such conditions are written over and below the arrow mark. So why don't we write the conditions in the reactants or the products? Because these conditions are not reacting, they are not the products, they are only helping the reaction to occur. Now, for example, you have KClO3, in the presence of the triangle that we write with a point on top, that is the one arrow going upwards, an upright triangle, it means it is heat. If you take potassium chlorate and you heat it in the presence of a catalyst, which is manganese dioxide, it results in the formation of potassium chloride and oxygen, which is solid and oxygen is a gas. Now, what have we done? If we have heated it, it obviously means the reaction must be endothermic. But we show the reaction, we show the heat on the arrow with the help of a triangle, and manganese dioxide, as I told you, is a catalyst. A catalyst is a substance which helps the chemical reaction to take place. It itself does not participate in the reaction, or we should say it gets involved in the reaction, it helps out, and later it goes away. It is not a part of the products. So manganese dioxide will combine with KClO3, it will help KClO3 to break down in the presence of heat, and then manganese dioxide, when it has broken down KClO3, it will move away. It has finished its work. It was only there to help KClO3 to break down into the products, that is KCl and oxygen. So such a substance is known as a catalyst. I often relate a catalyst to the role of a teacher in your life. Let us say that these two are the reactants and this is the product, and the catalysts are zinc oxide and chromium oxide. This is you, okay? And these are your books. And this is the educated you after education. So, and zinc oxide and chromium oxide, the catalyst is the teacher. The teacher comes, she helps you study your books, and as a result of that study, the teacher moves out. It stays at the school while you turn out to be what is the product of that education? You are an educated person. And you go away after getting your education. The product leaves. So a catalyst is a substance that helps the reactants to form the products without itself being a part of the reaction, because it separates out. It's neither a part of the reactants nor is it a part of the products. It's only a facilitator. It's only something that is helping out. So So the presence of a catalyst, you cannot write it in the reactants, you cannot write it in the product. So where will you write it? You will write it above or below the arrow mark. So here we had manganese dioxide, which was a catalyst. If you look at this reaction, you have carbon monoxide gas combined with hydrogen gas at 300 atmospheric pressure. You know, whatever pressure you are experiencing right now is 1 atmospheric pressure from the atmosphere. If you pressurize it 300 times, that much of pressure is required for this change to take place. 300 atmospheric pressure, and the temperature should be 300 degrees Celsius. At this temperature and at such a pressure, with the help of 2 catalysts, that is zinc oxide and chromium oxide, the carbon monoxide combines with hydrogen to form methanol. Right? That's how methanol is formed. Methanol, the formula for methanol is CH3OH. Then the next change, of course, as I had explained to you, is photosynthesis, where there are 6 carbon dioxide molecules, 6 molecules of water, and the carbon dioxide is present, the leaves take it from the atmosphere, and water, it absorbs it from the soil through the roots, and in the presence of sunlight and a pigment, green pigment in the leaves of plants, which is known as chlorophyll. So these are the conditions of the reaction. What results in the formation? It results in the formation of glucose, which is food, and oxygen, which is the source of oxygen for the entire living world. So this is how we make equations more informative. I think this is all for this video. I'll wrap up here. If you found the video helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. In the next video, I'm going to do balancing of chemical equations. So I'll be back in a minute. Thank you for watching, and bye-bye for now.